Tonight, we're going to try to answer a question that sounds simple until the moment you actually think about it. Does space ever end? 5 words. It sounds like something a child asks on a car ride and you'd expect a clean answer, but there isn't one. And the reason there isn't one is not because scientists haven't looked hard enough. It's because the question itself, once you really sit with it, starts to break apart in your hands. If you find comfort in these gentle explorations of space and science, I'd be grateful if you'd consider subscribing and giving this video a like. I'd love to know where you're watching from and what time it is for you. Feel free to drop your location and time in the comments below. Think about what you're actually asking. If space ends somewhere, what's on the other side? That's not a rhetorical provocation. That's a genuine problem. If you imagine flying a spacecraft in one direction, going for billions of years, and finally reaching some kind of boundary, some edge, some wall, you immediately have to ask what exists beyond it. If the answer is nothing, then nothing has to exist somewhere. It has to be located somewhere. And a located nothing is starting to sound a lot like something. If the answer is more space, then you haven't reached an edge at all. You've just moved through it. So what if space doesn't end? What if it just goes on forever in every direction, with no boundary, no limit, no final galaxy sitting at the edge of everything? That answer feels cleaner until you actually try to hold it in your mind. Infinite space. Space that genuinely never stops. Every distance you can name, and then beyond it, more. Our brains didn't evolve to handle that. We evolved to track distances measured in miles and hours, not concepts that go on without end. Infinity isn't a number you reach, it isn't a place. It's a statement that there is no place where things stop. And that's genuinely hard to think about without feeling something shift in your chest. Here's one way to feel the problem. Imagine you're standing in a completely dark room. No light at all, not even a glow from under a door. You can't see the walls. You don't know if they're 2 feet away or 200 feet away. You reach out and feel nothing. You take a step and feel nothing. You have no way of knowing whether the room is the size of a closet or the size of a stadium. That discomfort, that inability to locate yourself in relation to edges you can't detect, that's a small version of what cosmologists deal with every day. We're sitting inside the universe with instruments pointed outward, and we genuinely cannot tell whether the walls are close or whether there are no walls at all. What makes this question even harder is that we can only see so far. The universe has a horizon, not because space ends there, but because light travels at a fixed speed and the universe has only existed for a finite amount of time. Beyond that horizon there may be more, much more, or it may go on without end. We can't see it, our instruments can't reach it, and the part we can see, enormous as it is, tells us only so much about the part we can't. If you're the kind of person who finds questions like this fascinating, and I suspect you are, this channel is a place you'd want to stick around. If you want to keep exploring the deepest questions in science, consider showing your support with a like or by subscribing. It helps this reach more curious people, and it means a lot to have that support. Now, what we're going to do tonight is walk through what science actually says. Not what science wishes it could say. Not a clean resolution wrapped up at the end. What the evidence actually points toward, and where it runs out. We're going to talk about the geometry of space, what it means for the universe to have a shape, how measurements of the faintest light in existence have given us real data about the structure of everything that exists. We're going to talk about what scientists mean when they distinguish between a universe that is infinite and one that is finite but has no edge, which is a concept that sounds like a contradiction and isn't. Some of what we cover will remain unresolved by the time we're done. That's not a failure of the science, it's an honest picture of where humanity actually stands on one of the hardest questions we've ever tried to answer. The universe doesn't owe us tidy conclusions. It doesn't arrange itself for our comfort or our understanding. We ask, we measure, we build models, and sometimes the model says we don't know yet, and that's the most accurate thing it can say. So let's start at the beginning of the question. The raw, unsettling, genuine question. Does space ever end? And the answer, as best as science can give us right now, is one of the strangest things you'll ever hear. Let's start with something we can actually measure. The observable universe is at least 93 billion light years across. That's the portion we can actually see, not the whole universe, not everything that exists, just the part we're physically capable of detecting with our instruments. That number is so large it stops meaning anything the moment you read it. So let's build up to it. Let's start somewhere closer to home. The Earth has a diameter of about 7,900 miles. That feels large when you're standing on it. It takes a plane roughly 20 hours to fly from one side to the other. From space, though, the Earth is a small blue sphere, fragile looking, compact. You could fit about 1.3 million Earths inside the Sun. The Sun's diameter is roughly 864,000 miles. Light takes about 4.6 seconds to cross it from one edge to the other. Think about that. 4.6 seconds. The fastest thing in the universe, traveling at 186,000 miles per second. And it still needs nearly 5 seconds to get from one side of our Sun to the other. That's how large the Sun is compared to anything we experience in daily life. Now, let's go further. The Sun is about 93 million miles from Earth. Light covers that distance in roughly 8 minutes. So when you look at the Sun, you're not seeing it as it is right now. You're seeing it as it was 8 minutes ago. The outermost planet in our solar system, Neptune, orbits the Sun at a distance of about 2.8 billion miles. Light takes roughly 4 hours to travel from the Sun out to Neptune. Our entire solar system, from the Sun to the edge of the Oort cloud, spans somewhere around 100,000 astronomical units. Light would need more than a year just to cross it. And our solar system is one small system inside the Milky Way. The Milky Way is a barred spiral galaxy. It contains somewhere between 100 billion and 400 billion stars. Our Sun is one of them. One ordinary, medium-sized star, parked in one of the galaxy's outer spiral arms, about 26,000 light years from the center. The Milky Way itself is roughly 100,000 light years across. Light, traveling constantly at 186,000 miles per second, would need 100,000 years to cross our galaxy from one edge to the other. If you could somehow move at the speed of light the moment our species first appeared on Earth, you still wouldn't have made it halfway across the Milky Way by now. That's our galaxy. One galaxy. The Milky Way isn't alone. It belongs to a cluster of galaxies called the Local Group. The Local Group contains more than 50 galaxies, including our nearest large neighbor, the Andromeda Galaxy, which sits about 2.5 million light-years away. The light we receive from Andromeda tonight left that galaxy 2.5 million years ago. When it began its journey toward Earth, our ancestors were still making stone tools on the African savanna. The Local Group itself is about 10 million light-years across. Not 10 million miles, 10 million light-years. The Local Group sits inside a larger structure called the Virgo supercluster, which is about 110 million light-years across. Not 10 million miles, 10 million light-years. The Local Group sits inside a larger structure called the Virgo supercluster, which is about 110 million light-years across. The Virgo supercluster sits inside an even larger structure called Laniakea, a vast web of galaxy clusters and filaments spanning roughly 520 million light-years. Laniakea contains the mass of about 100 million billion suns. The number is too large to hold in your head. You can write it down, but you can't feel it. You can only keep scaling upward and try to get a sense of direction. And we're still nowhere near the edge of the observable universe. The observable universe stretches 46.5 billion light-years in every direction from us. That gives it a total diameter of about 93 billion light-years. Light crossing the observable universe would need 93 billion years. The universe itself is only 13.8 billion years old. So if light had started crossing the observable universe the moment the Big Bang occurred, it still wouldn't be done. It wouldn't even be close. Within that observable region, there are an estimated 2 trillion galaxies. 2 trillion. That's 2 trillion. Each of those galaxies contains hundreds of billions of stars. Some contain more. The Milky Way alone has up to 400 billion. There are galaxies out there with trillions of stars packed inside them. When you multiply 2 trillion galaxies by hundreds of billions of stars each, you get a number of stars in the observable universe that sits somewhere around a 10, followed by 24 zeros. Roughly 10 times more stars in the observable universe than there are grains of sand on every beach and desert on Earth. Every single one of those stars is a sun. Many of them have planets. Some of those planets sit in the right zone from their star for liquid water to exist on the surface. The observable universe is not mostly empty in any meaningful sense. It is filled, structured, layered. There are filaments of galaxy clusters stretching for hundreds of millions of light years. There are voids between them where almost nothing exists for equally enormous distances. The universe has a texture to it at the largest scales, a web-like structure, and every node of that web contains more suns than you could count in 1,000 lifetimes. Now remember, light crossing our sun takes 4.6 seconds. Light crossing the observable universe takes 93 billion years. That ratio gives you some sense of what we're dealing with. Our sun, which can swallow 1.3 million Earths, is so small compared to the observable universe that describing it as a grain of sand feels generous. It's closer to saying a single atom is sitting somewhere in a building the size of a city. The word observable is doing a lot of work in all of this. It doesn't mean the universe ends at 46.5 billion light years in every direction. The observable universe is not a wall or a boundary that space runs up against. It's a horizon, the limit of what we can see from where we're sitting, defined by the speed of light and the age of the universe. Beyond that horizon, the best current understanding says the universe keeps going. How far and in what shape is what the rest of this is about. But before we get there, sit with this for a moment. 2 trillion galaxies, hundreds of billions of stars in each one. Distances so vast that light from the nearest large galaxy left before humans existed. And all of that, every galaxy, every star, every atom of gas drifting between worlds, represents only the portion of the universe we're physically capable of observing. Now here's where it starts to get strange. We've established that the observable universe stretches roughly 93 billion light-years across. But that number raises an immediate problem. The universe is only 13.8 billion years old. So how can we see things that are 46 billion light-years away? If light has only had 13.8 billion years to travel, shouldn't the farthest thing we can possibly see be 13.8 billion light-years out? That's the intuitive answer. It's also wrong, and understanding why it's wrong is one of the most important things you can do if you want to actually understand the cosmos. The key is that space itself has been expanding the entire time those photons were traveling. Think about what that means. A photon leaves a distant galaxy 13 billion years ago. It's heading toward us. But while that photon is in flight, the space between us and that galaxy is stretching. The photon keeps moving forward. Space keeps pulling the destination further away. The photon still gets here eventually, but the source it came from is now much farther away than it was when the light first departed. By the time that light reaches our telescopes, the galaxy that sent it has been carried by expansion to a distance of over 46 billion light-years. We're seeing it as it was, not as it is, and where it is now is far beyond where it was when the light left. So the 46 billion light-year radius of the observable universe isn't a contradiction. It's a consequence of expansion happening the whole time. But here's what that means for the limit itself. There's a boundary beyond which we simply cannot see. Not because there's a wall, not because space ends, but because light from those regions hasn't had time to reach us yet. The photons are on their way. They've been traveling for billions of years. They'll keep traveling, but they started too far away in a universe that's been expanding too fast, and they haven't arrived. We're not missing anything because it doesn't exist. We're missing it because the universe is young and light is finite. Those regions are real. They're out there. We just can't see them. Think about standing on the deck of a ship in the middle of the ocean. You can see out to the horizon in every direction. The ocean appears to end at that line where the water meets the sky, but it doesn't. The ocean keeps going. The horizon is not the edge of the ocean. It's the limit of your line of sight from where you're standing. If you climbed a taller mast, the horizon would push further out. If you could somehow see around the curve of the earth, you'd find more ocean. The water doesn't stop. Your perspective does. The cosmic horizon works the same way. Light reaching us from the farthest observable regions has been traveling since very early in the universe's history. We see those regions as they were billions of years ago. Beyond that horizon, more universe exists. We have no direct evidence of what's out there, but we have no reason to think it stops. The horizon is a limit on our information, not a limit on space. Now here's the part that most people don't stop to consider. That horizon is personal. It belongs to us. It's centered on us. An observer sitting in a galaxy 1 billion light-years away from the Milky Way has their own horizon. Their observable universe is centered on them. It extends roughly 46 billion light-years in every direction from their position. That means large portions of their observable universe overlap with ours. We can both see the space between us, but their horizon reaches 1 billion light-years further than ours, in the direction away from us. They can see regions we can't, and we can see regions they can't. Their cosmic horizon and our cosmic horizon are not the same horizon. Every point in the universe has its own bubble, its own sphere of observable space, its own limit defined by the age of the universe and the speed of light. These bubbles overlap in complex ways depending on how far apart the observers are. Two galaxies close together share almost all of their observable universe. Two galaxies on opposite ends of the observable universe share almost none of it. There are almost certainly regions of the universe that are not inside anyone's observable bubble. Not ours, not any civilization's. Regions of space that exist, that contain galaxies and stars and perhaps planets, but that are causally disconnected from every observer everywhere. No signal from those regions has reached anyone. No information has escaped from them into the observable cosmos. They're there, isolated, unreachable, not because of distance in the ordinary sense, but because the universe expanded faster than light could carry news across the gap. Light travels at 186,000 miles per second. Nothing moves faster. But the expansion of space isn't movement in the ordinary sense. Space itself stretching isn't subject to the speed limit that governs objects moving through space. And in the early universe, expansion was happening at rates that overwhelmed the ability of light to keep up. The photons from those distant regions are still trying. They just started from too far away in a universe that's been working against them ever since. What this tells us is that the observable universe is not the universe. It's our window. It's the portion that has had time to communicate with us given the laws of physics and the age of everything. Beyond the window, more exists. How much more, we can't say. The window doesn't have a frame around it. The frame is just the present moment, and tomorrow the window is slightly larger as more light arrives from slightly farther regions that have finally had enough time to reach us. Every civilization in the universe, if any exist, is sitting at the center of its own bubble of observable space, and those bubbles don't fully overlap. Before we go any further, we need to deal with a problem buried inside the question itself. When most people ask whether space ends, they're picturing something specific. A wall. A boundary. Some kind of barrier you could theoretically fly a spaceship toward. close enough to press your hand against the surface and feel it push back. Maybe it's dark out there. Maybe the stars thin out. Maybe there's a kind of cosmic fence marking the edge of everything. That image feels natural. It's how we think about edges in everyday life. Rooms have walls. Countries have borders. Oceans have coastlines. So surely, if the universe is a thing, it has an edge. But this picture almost certainly doesn't match reality. And the reason it doesn't isn't just technical. The idea of a physical edge to space breaks down the moment you ask the simplest possible follow-up question. What's on the other side? If space ends somewhere, if you flew your spaceship far enough and eventually bumped into a wall, something has to be on the other side of that wall. You have two options. Either there's nothing out there, or there's something. Neither answer works the way you'd want. Say the answer is nothing, no space, no matter, no energy, just absolute nothing beyond the boundary. The problem is that nothing is already a thing we struggle to define. If there's a region of absolute nothing sitting right up against the edge of space, that region still occupies some kind of position. It's still somewhere, and if it's somewhere, then space in some sense extends into it. The idea collapses on itself. You've defined the edge of space, and then immediately implied there's something beyond it, even if that something is emptiness. Now say the answer is more space. You fly through the boundary and keep going, then it wasn't really a boundary at all, it was just a location. The universe kept going past it. There's no clean way out. Both answers unravel the concept of a physical edge before you've even gotten started. Scientists recognized this a long time ago. The question, where does space end, assumes a framework, that space is a container sitting inside something else, that it has an outer surface, that there's an inside and an outside. But that framework almost certainly doesn't apply to the universe. The universe isn't sitting inside something larger. There's no cosmic box. There's no surrounding void that space is carved out of. The universe is, by definition, everything that exists. There is no outside to speak of. So physicists and cosmologists don't really ask where space ends. They ask different questions, better questions, questions that actually have partial scientific answers. They ask, is the universe finite or infinite? And what is its shape? These sound like they might be the same as the original question. They're not. The distinction matters. A finite universe doesn't have to have an edge. Think about the surface of the Earth. It's finite. You could measure its total surface area. It covers a specific number of square miles, but there's no edge to it. Walk in any direction long enough and you don't fall off. You don't hit a wall. You come back around. The surface is finite and boundless at the same time. Those two things are not contradictions. They can coexist. The same logic can apply to the universe in 3 dimensions. A finite universe could have a definite total volume, a specific amount of space, without having a boundary anywhere inside it. You could travel in a straight line and never reach an edge. You'd just eventually come back to where you started, the way you'd circle the globe. An infinite universe is different. It just goes on. No boundary, no total volume you could measure, no coming back around. It extends forever in every direction without limit. Both possibilities, finite and infinite, get rid of the edge entirely. Neither one requires a wall. This is the reframing that scientists use, and it's the one we need to carry through the rest of this. We're not looking for the place where space stops. We're trying to figure out the geometry of space itself, whether it curves back on itself, whether it stretches flat in all directions without limit, whether it folds in ways our intuitions can't follow but our mathematics can describe. The shape of the universe determines whether it's finite or infinite, and the shape is something we can actually study. We can look at how light travels. We can measure the large-scale structure of galaxies. We can analyze the faint afterglow left over from the earliest moments after the Big Bang and read its temperature patterns the way you'd read a map. None of that tells us where the wall is because there probably isn't one, but it can tell us what kind of universe we're living in, and that turns out to be a far more interesting question. It's also worth pointing out how strange it is that the intuitive version of the question is the one that breaks down, while the abstract mathematical version is the one that holds together. Our instincts tell us that things have edges. Edges are everywhere in daily experience. But the universe doesn't seem to care about what's intuitive. The framework that actually describes space is one of geometry, curvature, and topology, not walls and fences. We're not looking for the edge of a room. We're trying to figure out what shape the room is, or whether room is even the right word at all. So the real question isn't whether space has a wall at the end, it's what shape space is, and whether that shape is finite or infinite. Einstein changed what we mean when we talk about space. Before Einstein, space was just the backdrop. It was the empty container that everything else existed inside. Newton treated it that way. Space was flat, fixed, and neutral. It didn't do anything. It just sat there while matter moved through it. Einstein looked at that picture and said it was wrong. His theory of general relativity, published in 1915, described something fundamentally different. Space isn't passive. Space isn't neutral. Space has a geometry, and that geometry can change. Mass warps it. Energy curves it. The path a beam of light takes through the universe isn't determined by some force pulling it sideways. It's determined by the shape of the space it's moving through. That was a completely new way of thinking about what space actually is, and once you accept it, the question of whether space ends stops being a question about walls and barriers. It becomes a question about geometry. There are three basic possibilities, three shapes that space, on the largest scales, could take. Each one has different properties. Each one has different implications for whether the universe is finite or infinite. And each one connects directly to what eventually happens to everything in it. This isn't abstract. The geometry of space is one of the most consequential facts about the universe that could possibly exist. Let's go through each one. The first possibility is a flat universe. When cosmologists say flat, they don't mean flat like a table. They mean flat in a geometric sense. They mean Euclidean. They mean the geometry you learned in school actually works. Parallel lines stay parallel. The angles inside a triangle add up to exactly 180 degrees. The shortest path between 2 points is a straight line. These things sound obvious. They sound like basic facts, but they're only true if space has zero curvature, and that's not guaranteed. Think about a piece of paper stretched out in every direction, infinitely. That's flat space. Draw 2 lines on it that are perfectly parallel, and those lines will never meet. They'll stay the same distance apart forever. No matter how far you extend them, they don't drift together and they don't drift apart. They just run alongside each other indefinitely. In a flat universe, that's how space works in 3 dimensions. It extends outward in every direction without bending, without curving back on itself. If it extends infinitely, it goes on forever. There's no wall, there's no edge. There's just more space in every direction, without limit. A flat universe could be infinite. It also, as it turns out, could be finite in ways that aren't immediately obvious. But we'll get to that. The key property of flat space is that zero curvature, and current measurements of the universe suggest that this is close to what we actually live in, close to flat, possibly exactly flat. The data points that direction. But close to flat and exactly flat are different things, and the universe is enormous, and measuring the curvature of something that large from a tiny position inside it is genuinely difficult. The second possibility is a positively curved universe, closed, spherical. This is the one that's easiest to visualize, even though the visualization is imperfect. Think about the surface of a sphere, a globe, a basketball, anything round. Now imagine you're an ant living on the surface of that sphere. From your perspective, the surface looks flat. You can't see the curvature. You just see a flat world extending in every direction. But the geometry is different. Draw 2 lines on the surface of that sphere that start out perfectly parallel. Follow them long enough, and they meet. Lines of longitude on Earth are a perfect example. At the equator, they run parallel. Follow them north and they converge at the pole. In positively curved space, parallel lines do the same thing. They come together. A triangle drawn on the surface of a sphere has angles that add up to more than 180 degrees. Not by much in a small triangle, but measurably more. And the sphere's surface is finite. It has a definite total area. You can't keep moving in the same direction forever without eventually coming back around to where you started. If the universe has positive curvature, it works the same way, but in 3 dimensions. The total volume of space would be finite. There would be no edge, no boundary you'd ever reach. But if you travelled far enough in any direction, you'd eventually loop back around and return to where you began. The universe would be like the surface of a sphere blown up to cosmic scales. Finite, but unbounded. That's a genuinely strange idea. A universe with a definite total size but no edge, no outside, just a closed space that curves back on itself. Now, a positively curved universe has implications for its future. In the original models, a universe with enough mass and positive curvature would eventually stop expanding. Gravity would win. The expansion would slow, halt, reverse. Everything would start contracting. The universe would collapse back inward, growing hotter and denser, ending in what cosmologists call the Big Crunch, a return to the conditions of the very beginning. Whether that scenario applies depends heavily on how much matter and energy the universe contains. We'll come back to that. The third possibility is a negatively curved universe. Open. Hyperbolic. This one is harder to picture because we don't have many good examples of it in everyday life. The closest thing is a saddle, or as some people describe it, the shape of a Pringle, a surface that curves upward in one direction and downward in another simultaneously. Extend that shape outward in every direction into 3 dimensions and you get hyperbolic space. In negatively curved space, parallel lines don't stay parallel, they drift apart. Draw 2 lines that start out running alongside each other, and over large distances they'll spread away from each other. A triangle in hyperbolic space has angles that add up to less than 180 degrees. The geometry is the mirror image of the spherical case in some ways. And a negatively curved universe would be infinite. Space would open outward, expanding, never looping back. There'd be no end. No finite total volume, just space spreading out forever in all directions. An open universe, in the older models, would expand forever. Gravity wouldn't be strong enough to reverse the expansion. The universe would keep growing, cooling, thinning out, until eventually stars burned out and everything faded. The geometry was thought to be directly tied to the fate. A closed spherical universe collapses. An open hyperbolic universe expands forever. A flat universe sits right on the boundary between those 2 outcomes, expanding but decelerating, theoretically coasting to a stop only after infinite time. That picture has been complicated significantly by the discovery of dark energy. The expansion of the universe is actually accelerating. That changes the long-term predictions regardless of geometry. But the geometric framework is still the foundation. The shape of space still tells you something deep about the structure of what exists. Here's what makes all of this more than a geometry lecture. These aren't just 3 abstract mathematical possibilities sitting in a textbook. One of them describes the actual universe we live in, the one you're in right now. Every atom in your body exists inside a space that has one of these 3 geometries, and whichever one it is, the implications are completely different. In one case, the universe is finite and closed, with a definite total size, possibly heading for a collapse. In another, it's infinite and open, expanding forever into an endless expanse. In the third, it's either infinite or wrapped into some complex shape we haven't detected yet. The geometry also determines whether there could be copies of everything we know. An infinite universe produces infinite repetitions. A finite one doesn't. The geometry shapes the question of whether the universe had a beginning in any meaningful sense, and whether it will have an ending. These are not small stakes. Cosmologists have spent decades trying to measure which of these three geometries the universe actually has. They've built satellites and pointed them at the oldest light in the universe. They've measured the positions and velocities of galaxies across billions of light years. They've tried to determine the shape of space from the inside, which is something like trying to determine the shape of a building you've never been outside of, using only the echoes of sounds bouncing off the walls. The current answer is flat, or very close to flat, but that answer comes with real uncertainty, and flat doesn't resolve the question of whether space ends. It just changes the terms of it. Which shape the universe actually has determines not only whether space ends, but what becomes of everything in it. And that's not a small question. The most precise measurements we have, satellites mapping the faint afterglow of the Big Bang, point toward a universe that is, at least locally, flat. That word, flat, sounds simple. It sounds almost disappointing, like the answer to a cosmic mystery turned out to be a geometry lesson. But flat, in this context, means something specific, and what it implies is anything but boring. When cosmologists say the universe is flat, they mean that the rules of standard Euclidean geometry hold, the rules you learnt in school. Draw two parallel lines and they stay parallel forever. Draw a triangle and its angles add up to exactly 180 degrees. Measure the circumference of a circle and it equals pi times twice the radius. These relationships, which seem obvious to us because we live inside a flat universe, are not guaranteed. They only hold in a universe with flat geometry. A universe with positive curvature would break all of them. The evidence for flatness comes from two major missions. WMAP, the Wilkinson Microwave Anisotropy Probe, launched in 2001 and spent years mapping the cosmic microwave background in extraordinary detail. Then came Planck, the European Space Agency satellite that pushed those measurements even further. What both missions found was consistent. The universe's curvature parameter sits within 0.4% of perfect flatness. That's a remarkably tight constraint. It means that if the universe has any curvature at all, it's so gentle, so slight, that we can't detect it with our current instruments. For practical purposes, space is flat. But here's what most people don't realize. Flat tells you the geometry. It doesn't tell you the topology. And those are two different things entirely. Geometry describes the local rules, how distances work, how angles behave, what parallel lines do. Topology describes the overall shape, the global structure, whether the universe wraps around on itself. And a flat geometry is compatible with more than one topology. Think about a sheet of paper. It's flat. The geometry is Euclidean. Now roll that sheet into a cylinder. The geometry hasn't changed. A triangle drawn on the surface of the cylinder still has angles that add up to 180 degrees. Parallel lines still stay parallel, but the global shape is now different. Travel far enough in one direction and you come back to where you started. The paper is still flat, but the space is now finite and it loops. That's what topology means. The local rules are the same. The overall structure is not. Now extend that idea. Take a flat square. Connect the left edge to the right edge. You get a cylinder. Then connect the top edge to the bottom edge. You get a torus, a donut shape. The geometry of a torus is still flat. Travel in any direction on the surface of that torus in a perfectly straight line, and you'll eventually return to your starting point. And yet, locally, everything looks flat. You'd have no way of knowing. The triangles check out. The parallel lines behave. From any small patch of that surface, it looks like a flat plane stretching outward forever. Our universe could be like that. A three-dimensional torus, spatially flat at every point, perfectly consistent with everything WMAP and Planck measured, and yet finite, bounded, looping back on itself in all three dimensions. If you travelled far enough in any direction, you'd eventually return to Earth from the opposite direction. You'd pass through the same galaxies again. You'd cross through the same regions of space on the other side that you already crossed through on this side. The universe wouldn't feel like it was looping. It would feel endless. But it wouldn't be. Scientists have looked for evidence of this. If the universe is a torus or any other topology that folds space back on itself, there should be signatures in the cosmic microwave background. Circles, patterns that repeat. If light from the early universe has had time to wrap all the way around and reach us from multiple directions, we should see matching rings in the CMB, the same temperature patterns appearing in different parts of the sky, pointing back to the same original region of space seen from different angles. Teams of researchers have searched for these circles. They've analysed the Planck data carefully, specifically looking for this kind of repeating structure. So far, they haven't found clear evidence of it. Not convincing evidence anyway, but they haven't definitively ruled it out either. If the universe is a torus, it might simply be too large. The repeating patterns might be out beyond our cosmic horizon, too far away for the light to have reached us yet, regardless of how long the universe has existed. That's the uncomfortable part. The absence of a detection doesn't close the case. If the topology scale, the distance at which the universe wraps around on itself, is larger than our observable horizon, we'd have no way of seeing the signature. We'd be stuck inside one copy of the repeating space, with no ability to look far enough to see where it connects. The universe could be finite and looping, and we'd be completely unable to tell. What we can say is this: the flatness result from WMAP and Planck is real and it's robust. It rules out strongly curved geometries. A highly positively curved universe, one with sharp, obvious spherical curvature, would have left clear signatures in the CMB patterns. Those signatures aren't there. Same for strong negative curvature. The universe isn't wildly bent in either direction. Whatever it is, at the scales we can measure, space is flat to a precision that's genuinely impressive. But flat is not the same as infinite. Flat is not the same as simple. A flat universe could stretch on forever in all three directions, never repeating, never looping, genuinely infinite. Or it could fold back on itself in a topology we haven't yet detected, finite but unbounded, with no edges and no walls but a definite total volume. Both are consistent with the data we have. Both are consistent with everything our best satellites have measured. A flat geometry doesn't answer the question of whether space ends. It just rules out certain ways that it could. But flatness isn't the only option, and the other possibilities are stranger, and in some ways more interesting. Let's start with the spherical model. In this version of the universe, space has what physicists call positive curvature. The geometry bends back on itself, the way the surface of a ball does. And the immediate implication of that is something most people find deeply counterintuitive. A spherical universe would be finite. It would have a definite total volume, but it would have no edge, no wall, no boundary you could ever reach. Think about what it means to walk on the surface of the Earth. The surface is finite. You can measure its total area, but you can walk in any direction for any distance and you will never fall off an edge. Eventually, you loop back around to where you started. The surface of the Earth doesn't end, it just curves back on itself. A spherical universe works exactly like that, except in 3 dimensions instead of 2. If you pointed a spaceship in any direction and travelled long enough, you wouldn't reach a wall. You wouldn't find empty space trailing off into nothing. You would, eventually, come back around to the place you started from. The universe would curve you back like a globe curves a ship. The geometry of this universe is fundamentally different from flat space. In a flat universe, if you draw 2 perfectly parallel lines and extend them forever, they stay parallel. They never meet. In a spherical universe, parallel lines converge. They bend toward each other and eventually intersect. You can see this on a globe. Lines of longitude are parallel at the equator. By the time they reach the poles, they've crossed. Draw a triangle on the surface of a sphere, and its 3 angles add up to more than 180 degrees. On a flat surface, they add up to exactly 180. That difference is small, but it's real, and it tells you something fundamental about the shape of the space you're living in. Now scale that up to the entire universe. If space has positive curvature, then any triangle you could draw across cosmic distances would have angles summing to slightly more than 180 degrees. The lines of light travelling between distant galaxies would gently, imperceptibly bend toward each other, and the universe, despite being finite, would have no edge anywhere. Every direction is equally valid. No location is more central than any other. There's no centre, there's no boundary, there's just the surface, curving everywhere, looping back on itself. The total volume of a spherical universe would still be staggering. We're not talking about something small. Even if the curvature were very gentle, the universe could be many times larger than the portion we can observe. Finite doesn't mean small, it just means not infinite. If the universe was spherical, we might eventually detect evidence of this closed geometry through careful observation. Patterns might emerge in the distribution of distant galaxies and clusters. The cosmic microwave background radiation itself might show subtle correlations that suggest a wrapped-around geometry. These signatures would be faint, hidden within vast data sets, and extraordinarily difficult to isolate from other sources of variation. But astronomers have developed sophisticated statistical methods to search for exactly such patterns. Then there's the other possibility, the hyperbolic universe. This one is harder to picture because nothing in everyday experience looks quite like it. The closest analogy is a saddle, or if you prefer, the shape of a potato chip. The surface curves upward along one axis and downward along the other simultaneously. That's negative curvature. And in a hyperbolic universe, space does that in every direction all at once. The geometry here goes the opposite direction from the spherical case. Parallel lines don't converge, they drift apart. The farther they travel, the greater the distance between them. Draw a triangle in hyperbolic space, and its angles add up to less than 180 degrees. Space is opening up, always spreading, never folding back. A hyperbolic universe would be infinite. The structure of negatively curved space doesn't allow for a closed finite geometry the way a sphere does. The saddle just keeps going, curving outward, spreading in every direction without limit. If we lived in a hyperbolic universe, space would go on forever, and there would be no possibility of looping back around to your starting point. You could travel in a straight line for all of time and never return. A hyperbolic geometry creates a universe fundamentally unlike both flat and spherical models. Expansion accelerates at larger scales, and distances multiply in peculiar ways. The sheer volume of such a universe grows incomprehensibly fast. Two observers moving apart would find the space between them expanding ever more rapidly. The vast majority of the hyperbolic universe would remain forever unreachable, not because of time's limitations alone, but because the structure of space itself pushes regions apart with increasing vigor. Now, here's where things get uncomfortable. Current observations favor neither of these models. The measurements from the cosmic microwave background point toward a flat universe, not a spherical or hyperbolic one. Both of these possibilities are, at the moment, disfavored by the data. But disfavored is not the same as ruled out. And this is where the uncertainty matters. Our measurements have error margins, tiny ones, but real ones. The Planck satellite measured the universe's curvature to within a fraction of a percent, and within that margin, space appears flat. But within that same margin, a very slight curvature in either direction would still be consistent with the data. We haven't measured flatness with enough precision to say the curvature is exactly zero. We've measured it with enough precision to say the curvature is very close to zero. Those are different statements. A universe with very gentle positive curvature, a sphere so enormous that its surface appears locally flat, would look exactly like a flat universe at the scales we can observe. This is the same reason Earth looks flat when you're standing in a field. You're not seeing enough of the surface to notice the curve. The horizon is too close. You need to zoom out far enough before the spherical geometry becomes apparent. We could be in that situation right now. We could be living inside a spherical universe so vast that our entire observable bubble, 93 billion light-years across, represents only a tiny fraction of the total surface. From inside that bubble, space would look flat. Every measurement would come back consistent with flatness. Every parallel line would appear to stay parallel across the distances we can measure. And we would have no way of knowing that, far beyond our horizon, those lines were slowly, quietly beginning to converge. The universe could be very gently curved in ways our instruments can't yet detect. We're measuring a tiny patch of something potentially vast, and a tiny patch of a sphere looks flat too. To understand where the space ends, you have to understand where space came from. And that takes us back 13.8 billion years to the beginning of everything. Most people carry around a mental image of the Big Bang, a single point, a fireball, an explosion hurling matter outward in all directions through empty space. It's a vivid picture. It's also wrong. Not slightly wrong. Fundamentally wrong in a way that changes everything about how you think about the universe. The Big Bang was not an explosion that happened inside space. It was an expansion of space itself. There was no empty room for it to explode into. Space came into existence and grew. That distinction matters more than almost anything else in cosmology. Here's what that actually means. Before the Big Bang, there was no space. There was no time. There was no empty void waiting to be filled. The concepts we use to describe location and duration simply didn't exist. When the universe began, space and time began with it. Every point that exists in the universe today was part of that beginning. Not just one point. Every point. The Big Bang didn't happen somewhere in particular. It happened everywhere, all at once. There is no location you could travel to and say, this is where it started here. Every location in the universe is equally the origin. You are sitting at the origin of the Big Bang right now. So is a galaxy 10 billion light years away. So is everything in between. Think about what that means for the question of whether space has an edge. If the Big Bang happened everywhere simultaneously, there's no center. And if there's no center, there's no edge defined relative to that center. The universe didn't expand outward from a single point the way a grenade sends shrapnel flying. It expanded from itself in all directions at every location at once. Now, what was actually happening in those first moments? The temperatures and densities involved are beyond anything our instruments can produce. In the first fraction of a second, the universe was unimaginably hot. We're talking about temperatures of trillions of degrees, not millions, trillions. At those temperatures, the fundamental forces of nature that we experience as separate things today were unified into a single force. Gravity, electromagnetism, the strong nuclear force, the weak nuclear force, all merged together into something our physics can describe only partially. As the universe expanded, it cooled. As it cooled, those forces separated from each other, one by one, like phases of matter freezing out at different temperatures. In the first second, protons and neutrons formed from the raw soup of quarks and gluons that filled everything. Within the first few minutes, those protons and neutrons began fusing into the nuclei of the lightest elements: hydrogen, helium, trace amounts of lithium. This process is called Big Bang nucleosynthesis. The universe was a giant fusion reactor, and it ran for about the first 20 minutes before cooling too much for fusion to continue. The ratio of hydrogen to helium produced during that window matches exactly what we observe in the oldest stars today. That's one of the strongest pieces of evidence we have that our model of the early universe is correct. But here's where the model hits a wall. Go back far enough, close enough to the very beginning, and the equations break down. Physicists call this the singularity. It's the point in our mathematics where density becomes infinite, temperature becomes infinite, and our laws of physics stop making useful predictions. It's not that something strange happened at the singularity and we just haven't figured out what yet. It's that our current understanding of physics, general relativity, quantum mechanics, cannot be applied there. The two great theories of modern physics contradict each other at those extremes. We need a theory of quantum gravity to describe what was happening, and we don't have one yet. So when people ask what happened before the Big Bang, The honest answer is that we don't know. And there's a deeper problem than just not knowing. The word before might not even apply. Time, as far as we can tell, emerged from the Big Bang along with space. If time began at the Big Bang, asking what happened before it is like asking what is south of the South Pole. The question assumes a direction that doesn't exist from that location. Stephen Hawking used exactly that analogy. It isn't a dodge, it's a genuine feature of the geometry of space-time. Some physicists have proposed frameworks that try to get around this. One idea is that the universe has always existed in some form, that the Big Bang was not the absolute beginning but a transition from a previous state. Maybe a previous universe collapsed and bounced. Maybe the Big Bang emerged from a quantum fluctuation in some deeper structure. These are serious proposals made by serious scientists, and they're genuinely interesting, but none of them are confirmed. They're speculative frameworks, constrained but not proven by evidence we currently have. What we do know is that the early universe was almost perfectly smooth. When we look at the cosmic microwave background, the faint afterglow of the early universe, we see temperatures that are uniform across the entire sky to about 1 part in 100,000. Regions of the sky that appear to have no way of ever being in contact with each other are still at almost exactly the same temperature. That smoothness is a puzzle. It suggests that the regions we see today were somehow in equilibrium with each other very early on. One proposed explanation is inflation, a period of incredibly rapid expansion in the first tiny fractions of a second, where the universe grew by an enormous factor almost instantaneously, smoothing out any irregularities. Inflation also helps explain why the universe looks flat. When we say the universe is flat, we mean its large-scale geometry follows the rules of flat Euclidean geometry, the kind where parallel lines never meet and angles in a triangle add up to 180 degrees. A flat universe extends infinitely in all directions without boundary or edge. But the universe's shape could theoretically be different. It could have positive curvature like a sphere, meaning if you travelled far enough in one direction, you'd eventually return to your starting point, or negative curvature like a saddle. The key insight is that space's geometry isn't imposed from the outside. It's determined entirely by the matter and energy within the universe itself. The observations we currently have strongly suggest our universe is flat, meaning space likely extends without end. The point is that even the smoothness we observe is a clue pointing back to a beginning that was both violent and almost perfectly uniform. The tiny variations that did exist in that early smoothness matter enormously. Not perfectly smooth, almost perfectly smooth. Those tiny fluctuations, 1 part in 100,000, were the seeds of everything. Gravity pulled slightly denser regions together over hundreds of millions of years. Those regions collapsed into the first stars. Stars clustered into galaxies. Galaxies clustered into the large-scale structure we see today, filaments and walls and voids stretching across billions of light years. Every galaxy, every star, every planet, every atom in your body traces back to a tiny ripple in the density of the early universe. The fact that the universe was not quite perfectly smooth is the reason anything interesting exists at all. So when we ask whether space ends, we're asking a question about something that came into existence 13.8 billion years ago, expanded from every point simultaneously, produced structure from near-perfect uniformity, and has been growing ever since. It didn't start somewhere and spread outward. It started everywhere and expanded from itself. That's the foundation everything else rests on. The universe didn't explode into existing space. Space itself exploded into existence. And asking what existed before it is like asking what's south of the South Pole. Here's a question that sounds simple and isn't. If the universe is expanding, what is it expanding into? Most people hear that the universe is expanding and immediately picture something like a balloon inflating inside a room. The balloon gets bigger. The room was already there. The balloon expands into the room. That feels intuitive. That feels like how expansion works. But that picture, as useful as it is to start with, leads you directly into a wall. Let's actually use the balloon. Draw some dots on the surface of a deflated balloon, scattered randomly, spread all across it. Now inflate it. Watch what happens to the dots. Every single dot moves away from every other dot, not because the dots themselves are moving across the surface, but because the surface between them is stretching. And here's the part that matters. No dot is at the center of that expansion. There's no single dot you can point to and say that one is where the expansion is coming from. From the perspective of any dot on that balloon, everything else is moving away. Every dot sees itself as the center. None of them are. That's the key insight the balloon analogy gives you. The expansion isn't a movement through space. It's a stretching of space itself. Galaxies aren't flying outward through some pre-existing void. The space between them is growing. There's a difference, and the difference matters enormously. Edwin Hubble understood this before most people were even asking the question. In the 1920s, Hubble was studying galaxies, or nebulae as they were still being called, and he noticed something strange. Almost all of them showed a redshift in their light. The light coming from distant galaxies was stretched toward the red end of the spectrum, which meant those galaxies were moving away from us. And the pattern wasn't random. The farther away a galaxy was, the faster it was receding. Hubble published these findings, and they fundamentally changed our picture of the universe. The universe wasn't static, it wasn't stable, it was expanding in every direction at once. And if you ran the clock backward, if you reversed that expansion, everything converges. The universe was once smaller, much smaller, dense and hot and compressed into a state we can barely describe. That's what the evidence pointed to. Not a universe that had always been this way. A universe with a history. A universe that used to be different. But back to the balloon, because here's where it breaks down. The balloon's surface is two-dimensional. When it inflates, it expands into three-dimensional space. The space inside the room, the space around it. There's a higher dimension that the balloon's surface is expanding into. You can see it. You can point to it. The analogy only works because we're standing outside the balloon, watching from three dimensions. Our universe is three-dimensional space, and as far as we can tell, it is not expanding into a higher dimensional space the way the balloon's surface expands into the room. There is no room. There is no outside. The expansion of the universe isn't happening inside something larger. The universe isn't inflating into empty space that was already waiting for it. The space is all there is, and the space itself is stretching. That's genuinely hard to hold in your head. Our brains didn't develop any machinery for thinking about this. We evolved to track motion through space, not the expansion of space itself. We understand things moving inside a container. We don't have an intuition for the container growing when there's nothing outside the container. This conceptual difficulty has haunted cosmology for decades. Philosophers and physicists alike have grappled with the seeming impossibility of infinity itself growing. How can something without boundaries expand? If the universe contains everything, what does it mean for everything to become more spread out? These questions reveal the limits of our language as much as our intuition. We use words like expansion and stretching, borrowed from everyday experience. But those words carry baggage. They imply a process happening within or into something else. Yet the universe offers no such framework. The expansion is fundamentally self-referential. Space grows, which means distances between things increase, but there's nowhere for that growth to occur, except within space itself. Mathematically, cosmologists can describe this without any trouble. The equations handle it cleanly. There's no contradiction, no paradox, no hidden assumption that breaks the logic. The math works. It's only the visualization that fails. And the reason it fails is that the visualization requires you to imagine a view from outside, and there is no outside. Some physicists have asked whether the universe might be embedded in some higher dimensional space, a kind of cosmic superstructure that our universe exists within. It's not an impossible idea. But here's the problem. Even if that were true, even if there were some higher dimensional space our universe was expanding into, that space would be entirely unobservable. No signal from it could reach us. No measurement we could ever make would detect it. It would be real in a theoretical sense and invisible in every practical sense. So when we talk about what the universe is expanding into, the honest answer remains the same. Nothing we can observe or measure. Think about what that actually means. Every direction you look, space is stretching. Distant galaxies are being carried away from us, not because they're moving through space, but because the space between here and there is getting larger. And because this is happening everywhere simultaneously, there's no edge to the expansion, no front line where the universe is pushing into something else. The expansion doesn't have a direction. It doesn't have a leading edge. It's happening at every point, in every location, all at once. The dots on the balloon understood this better than most. None of them were moving. The surface just grew. What Hubble's observations gave us was more than a discovery about galaxies moving apart. They gave us the clearest evidence that the universe has a past, a denser, hotter, younger past, and that it's been evolving ever since. The expansion he measured has been confirmed and refined across a century of observations. We can measure how fast different galaxies are receding. We can map the expansion across billions of light years. We can trace it backward and forward in time. And still, the question of what space is expanding into sits there, unanswered. Not because scientists haven't thought carefully about it, because the question may not have an answer in any terms we can observe or test. The universe is self-contained in a way that our everyday experience gives us no preparation for. There's no outside edge, no surrounding void, no bigger space holding everything in place. The expansion is real, the evidence is overwhelming, and yet what space is expanding into, if anything, remains one of the most genuinely unanswerable questions in all of physics. So what does science actually say about whether the universe is infinite? Most cosmologists, when pressed, will lean toward infinite, not with certainty. Not with the kind of confidence they'd attach to, say, the age of the universe or the speed of light, but when you survey the field, the weight of opinion tilts in that direction. The reasoning isn't mystical. It follows directly from the data we have and what that data fails to show us. Here's the core of the argument. If the universe is finite, if it wraps around on itself like a sphere or a torus, then light traveling through it would wrap around too. You'd expect to find repeating patterns in the cosmic microwave background, certain arrangements of hot and cold spots that appear in multiple locations on the sky, mirrored across vast distances like looking at a room tiled with the same wallpaper in every direction. Cosmologists have a name for what to look for. They call them circles in the sky. If the universe closes back on itself, the signal of that closure should appear in the earliest light we can observe. Scientists have searched for those circles. They've combed through the CMB data from WMAP and Planck, two satellites that mapped the early universe in extraordinary detail. They haven't found convincing evidence of repeating topology. Not yet. But here's what that absence doesn't prove. It doesn't prove the universe is infinite. The universe could be finite and simply too large for the repeating patterns to fall within our observable horizon. If the universe is a closed sphere, but that sphere is 100 times larger than what we can see, the repeated images would be sitting out there beyond our reach. We'd have no way to detect them. The absence of circles in the sky rules out certain sizes of finite universe, specifically ones small enough that the wrapping effect would be visible to us. It doesn't rule out a finite universe in general. It just means that if the universe is finite, it's enormous, vastly larger than the 93 billion light-years we can observe. So where does that leave us? Scientists are left with two options, neither of which is provably wrong. Either the universe is infinite, going on forever in all directions with no boundary of any kind, or it's finite, but so unimaginably large that the distinction barely matters from where we're standing. Some physicists will tell you those two options are, for all practical purposes, the same thing. If the universe is finite but larger than we could ever observe or interact with, Calling it finite instead of infinite feels almost like a philosophical preference rather than a scientific one. The part that matters to us, the part we can ever reach or measure, is effectively infinite either way. Think about what infinite actually means here, though. Not infinite in the vague way we sometimes use the word to mean very big. Mathematically, literally infinite. No end, no last galaxy, no final stretch of empty space beyond which there is nothing. If the universe is infinite in extent and roughly uniform, which it appears to be at the largest scales we can see, then everything that can happen does happen somewhere. An infinite universe with matter distributed throughout it means infinite matter. Infinite matter arranged by physics means infinite stars, infinite planets, infinite versions of every configuration of atoms that is physically possible. That includes Earth. An infinite universe almost certainly contains other planets that are, atom for atom, identical to Earth. Not similar, identical. It contains other versions of you, sitting somewhere unimaginably far beyond the observable horizon, reading the same words, thinking the same thoughts. It contains versions of you that made every different decision you've ever faced, because an infinite universe contains every arrangement of matter that physics permits, and all of those arrangements exist somewhere. This is not science fiction. It's not speculation in the casual sense. It's a direct mathematical consequence of applying infinity to a universe with physical laws. If you have infinite space and finite rules, every possible configuration repeats infinitely. That's uncomfortable. It should be uncomfortable. Our intuitions were built for a world of finite things, finite rooms, finite distances, finite lifetimes. Infinity doesn't fit neatly into the brain. It fits into equations. But the discomfort doesn't make it wrong. There's a version of the finite universe argument that some people find more reassuring. The idea that the universe is closed, bounded, self-contained. That it has a definite total volume, even if that volume is beyond anything we can picture. That there is in principle a number you could write down for how much space exists. This is a universe you can hold in your mind as a concept, even if not in your hands. It has edges in the mathematical sense, not walls but limits on total extent. It's the kind of universe that feels like it belongs to the same category as other things we understand, finite things. But the evidence doesn't particularly favor that interpretation. The universe, as best we can measure it, is spatially flat, and a flat universe, extending uniformly in all directions with no detectable curvature, is most naturally infinite. Not necessarily, but most naturally. A flat geometry fits most easily onto an infinite space. A finite flat universe requires a specific topology, a way of connecting the edges back to each other, and that topology would leave traces in the CMB that we haven't found. So scientists are left holding a probability, not a certainty. The honest position is that the universe is probably infinite, or effectively so, but we can't prove it. The tools we have, even the best satellites, even the most precise measurements of the cosmic microwave background, sample a finite region. We are, in the end, observers sitting inside a bubble of light we can see, making inferences about what lies beyond it. Those inferences are guided by physics and mathematics and decades of careful measurement. They're the best inferences our species has ever made about anything, and they point tentatively towards something without end. The idea of a finite universe is comfortable and imaginable, but the evidence, such as it is, leans towards something much harder to sit with. The most detailed picture we have of the early universe, and by extension of the universe's shape, comes from light that has been travelling toward us for nearly 13.8 billion years. Not light from stars, not light from galaxies. Light from the universe itself, from a moment when everything was so hot and so dense that matter and energy were packed together in a single glowing plasma, opaque in every direction, like the inside of a star. That state lasted for roughly 380,000 years after the Big Bang. Then something changed. The universe cooled enough that electrons and protons could combine into hydrogen atoms for the first time. And when that happened, the universe became transparent. Photons that had been trapped, bouncing endlessly off charged particles, were suddenly free to travel. They streamed outward in every direction. They have been traveling ever since. That light is what we call the cosmic microwave background, the CMB. It fills the sky in every direction uniformly at a temperature of about 2.7 degrees above absolute zero. We can't see it with our eyes. It exists at microwave wavelengths far below visible light. But with the right instruments, we can map it in extraordinary detail. And what those maps show us is a snapshot of the universe as it existed 380,000 years after the Big Bang. Not a model, not a simulation, actual light from that actual moment, finally arriving at our detectors after traveling for nearly the entire age of the universe. Think about what that means for a moment. The universe was 380,000 years old when that light was released. The universe is now 13.8 billion years old. That light has been crossing space for almost the entire history of everything, and we can catch it, we can measure it, we can read information out of it the way a geologist reads information out of ancient rock strata. The CMB is the oldest light we will ever be able to see. Nothing older exists. Before the universe became transparent, light couldn't travel freely, so there's no earlier signal for us to detect. The CMB is the absolute beginning of our visible record. What makes it so valuable is the detail buried inside it. On the largest scales, the CMB looks almost perfectly uniform. The temperature is the same in every direction, within a tiny fraction of a degree, but not perfectly uniform. There are fluctuations, temperature differences of about 1 part in 100,000, patches of sky that are slightly warmer, patches that are slightly cooler. These differences are small enough that early instruments missed them entirely. Detecting them required satellites designed specifically for the task. COBE in the early 1990s saw them for the first time. WMAP refined the picture. The Planck satellite, launched in 2009, produced the most detailed CMB map we've ever made. Those tiny fluctuations are not noise, they're structure. They represent regions of the early universe that were slightly denser than average, and regions that were slightly less dense. Gravity would eventually pull the denser regions into the galaxies and galaxy clusters we see today. The pattern of fluctuations in the CMB is directly connected to the large-scale structure of the universe billions of years later. By analyzing the size and distribution of those fluctuations, scientists can extract information about the geometry of space, the composition of the universe, and the physical processes that were operating in the first moments after the Big Bang. The geometry information comes from something specific. The fluctuations in the CMB have a characteristic scale. There's a typical size for the hot and cold patches, and that size depends on the curvature of space. If space is flat, the patches appear at a certain angular size on the sky. If space is positively curved, they appear larger. If space is negatively curved, they appear smaller. When astronomers measured the angular size of those patches precisely, the result matched the prediction for a flat universe. Not approximately flat. Flat to within about 0.4%. That's an extraordinary level of precision for a measurement of the entire universe made from a single planet in one small corner of the Milky Way. The same data tells us what the universe is made of, about 5% ordinary matter. The atoms, molecules, stars, planets, gas, dust, everything we've ever seen or touched. About 27% dark matter, something that has gravity but doesn't interact with light, whose nature we still don't understand, and about 68% dark energy, the mysterious quantity driving the accelerating expansion of space. These numbers come directly from fitting the observed CMB fluctuation pattern to theoretical models. The fit is remarkably precise. The CMB has told us more about the large-scale contents of the universe than any other single source of data. But here's what the CMB cannot tell us. It cannot tell us whether the universe is finite or infinite. It can constrain the possibilities. Certain shapes are ruled out. If the universe were a small torus or a small sphere, meaning small enough that light could have wrapped all the way around it and reached us from multiple directions, we would expect to see repeated patterns in the CMB, matching circles, identical patches appearing in different parts of the sky. Astronomers have searched for those patterns. They haven't found them, at least not convincingly. That tells us something. It tells us that if the universe wraps back on itself, it does so on a scale larger than our observable horizon. The topology, if it exists, is hidden from us. The universe could still be finite. It could be a sphere or a torus of enormous size, large enough that no light has ever completed a full loop. We wouldn't know. The CMB can't reach beyond our horizon, and topology evidence beyond that horizon is, by definition, invisible to us. So we're left with a boundary. The most powerful observational tool in cosmology has given us flat geometry, precise composition, and an ancient snapshot of the universe that no other instrument can match. Every measurement narrows the possibilities, but the maps we've made of the earliest light in the universe still haven't told us whether everything we can see is everything there is. In the late 1990s, astronomers set out to measure how fast the universe's expansion was slowing down, and discovered it wasn't slowing down at all. This wasn't a small surprise. It wasn't a result that made scientists scratch their heads and tweak a number. It was a complete overturning of what everyone expected to find. Gravity pulls things together. The universe is full of matter. Matter produces gravity. So naturally, the expansion that started with the Big Bang should be coasting to a slower and slower pace, like a ball thrown into the air gradually losing speed. That was the assumption. Two independent teams of astronomers were racing to confirm it. They were using distant supernovae as measuring tools, a specific type called Type 1a supernovae, which always explode with roughly the same intrinsic brightness. If you know how bright something actually is, and you measure how bright it appears from Earth, you can calculate its distance. Both teams did this. Both teams got the same answer. The supernovae were dimmer than they should have been. They were farther away than the models predicted. The universe wasn't slowing down, it was speeding up. That result, published in 1998, changed cosmology permanently. The teams were awarded the Nobel Prize in Physics in 2011. And the thing driving the acceleration, whatever it is, got a name: dark energy. Dark energy is estimated to make up about 68% of the total energy content of the universe. Ordinary matter, everything you can see and touch, every planet, every star, every galaxy accounts for about 5%. Dark matter, which we can't directly observe but can detect through its gravitational effects, makes up roughly 27%. That leaves dark energy as the dominant component of the universe by a wide margin. The majority of everything that exists, in terms of energy, is something we cannot detect, cannot produce, and cannot explain with any satisfying theoretical framework. And that's the part worth sitting with. We don't know what dark energy is. Not in the way that scientists sometimes say they don't know something while having a fairly good working model. This is different. There is no good working model. The leading description is called the cosmological constant. It treats dark energy as a fixed energy density built into space itself. Not a substance moving through space, but a property of space, present everywhere, in every cubic centimeter of vacuum, at a constant value. As space expands, more space comes into existence, which means more of this energy, and more energy means more acceleration. The expansion feeds itself. The cosmological constant has an ironic history. Einstein introduced it into his equations in 1917. He needed it to make his model of the universe static, because at the time, no one knew the universe was expanding. When Hubble's observations in the 1920s made it clear that the universe was in fact expanding, Einstein called the cosmological constant his greatest blunder and removed it from his equations. Decades later, the universe turned out to need it after all, not to keep things static, but to explain why everything is flying apart faster and faster. What makes dark energy so difficult to understand is that it behaves in a way nothing else does. Every other form of energy we know about dilutes as space expands. Pour matter into a larger volume, and the density drops. The same happens with radiation, but dark energy stays constant. Its density doesn't change as space grows. It just persists, uniform and unchanging, filling every part of space equally. That behavior is strange enough to make physicists deeply uncomfortable. Quantum field theory predicts that empty space should have an energy density, but the predicted value is off from the observed value by a factor of somewhere around 10 to the 120th power. That is the largest discrepancy between theory and observation in the history of physics. Something is wrong with our understanding, and we don't yet know what. Some researchers have explored whether these quantum inconsistencies point to undiscovered physics beyond our current theories. The vacuum itself may contain layers of complexity that standard quantum mechanics has not yet revealed. These hidden properties could fundamentally change how we understand the relationship between space, energy, and the structure of reality itself. There are alternatives to the cosmological constant. Some physicists propose that dark energy is not a fixed property of space, but a dynamic field that changes over time, something called quintessence. In this model, the strength of dark energy could vary across cosmic history, and understanding how it changes might eventually explain its origin. Other proposals involve modifications to general relativity itself. None of these alternatives currently have strong observational support over the cosmological constant. The data fits the simplest model, which is a fixed value, but a fit to current data is not the same as an explanation. The implications of accelerating expansion go far beyond abstract physics. They have direct consequences for what will eventually be observable from any point in the universe. Right now, galaxies beyond a certain distance are already receding from us faster than the speed of light. This doesn't violate relativity because it's space itself stretching, not objects moving through space. But the practical result is the same. Light from those galaxies can never reach us. They are already beyond our reach permanently. As the acceleration continues, more and more galaxies will cross this threshold. The cosmic horizon will slowly contract in terms of what we can ever communicate with or receive information from. Trillions of years from now, the picture will be stark. The Milky Way will have merged with Andromeda and several other nearby galaxies into a single structure. Beyond that structure, the sky will be dark. Every other galaxy in the universe will have been carried beyond the horizon by the accelerating expansion of space. A civilization living in that distant future, looking out into the universe, would see nothing beyond their own galaxy. They would have no way of knowing that billions of other galaxies had ever existed. The evidence would be gone. The light would be too redshifted to detect, or simply too far away to ever arrive. We're in an unusual position right now. We can see roughly 2 trillion galaxies in the observable universe. We have their light. We can study their spectra, measure their distances, reconstruct the history of the universe across 13.8 billion years. That window is not permanent. It is slowly closing. The accelerating expansion is pulling the evidence away from us, one galaxy at a time, across timescales so vast they're difficult to express in any meaningful way. But the direction of things is clear. Whatever dark energy is, it means the universe is not only expanding, but accelerating away from itself, and that has consequences for any future civilization trying to understand the cosmos. There's a theory that makes the question of whether space ends even stranger, and it starts with something that happened in the first 10 to the negative 32 seconds after the Big Bang. That's not a typo. 10 to the negative 32nd power. A fraction of a second so small it has no real name in ordinary language. In that unimaginably brief window, something happened to the universe that changed everything about its structure. Physicists call it inflation. Not the gradual expansion the universe has been doing ever since, but something far more violent. A period of exponential growth so rapid that the universe went from smaller than a single proton to something approaching cosmic scale in almost no time at all. Think about that. The entire observable universe, every galaxy, every star, every atom, compressed into something smaller than a particle, and then stretched outward at a rate that dwarfs anything we can point to in nature. Inflation was first proposed in 1980 by physicist Alan Guth. He wasn't trying to answer the question of whether space ends. He was trying to solve a different set of problems entirely, 3 of them specifically. And the fact that inflation solved all 3 at once is part of why physicists take it so seriously. The first problem is called the horizon problem. Look at opposite ends of the observable universe. Those regions are separated by roughly 93 billion light years. They have never been in contact. Light couldn't have travelled between them in the age of the universe. And yet, when we measure the temperature of the cosmic microwave background in those 2 directions, it's almost identical. Same temperature, same properties. Regions that should have no knowledge of each other are in near perfect agreement. That's strange. Without inflation, there's no good explanation for it. With inflation, those regions were once close enough to reach thermal equilibrium before the expansion tore them apart. The uniformity we see today is a fossil of that early connection. The second problem is flatness. As discussed earlier, the universe appears to be spatially flat to extraordinary precision, but flatness is an unstable condition. In the early universe, any slight deviation from perfect flatness would have amplified over time, sending the universe either into rapid collapse or runaway expansion. The fact that we're still here, with a universe that looks so flat, means the early universe must have been flat to an almost unbelievable degree of precision. Inflation explains this. Rapid exponential expansion smooths out curvature the same way inflating a balloon smooths out wrinkles on its surface. Whatever curvature existed before inflation, the expansion flattened it. The third problem involves exotic particles. According to the physics of the early universe, the conditions right after the Big Bang should have produced enormous numbers of magnetic monopoles, strange, hypothetical particles that act like a single pole of a magnet. We've never detected one. Inflation pushes the answer here too. If inflation happened, it diluted the density of these particles so dramatically that finding one today would be essentially impossible. They're out there perhaps, just spread across a volume of space so vast that none has ever crossed our path. 3 separate puzzles, 1 proposed mechanism. That's a strong argument. But here's where the theory takes a turn that changes the meaning of the question we started with. Not all versions of inflation end cleanly. In many theoretical models, the process that drives inflation, a hypothetical energy field physicists call the inflaton field, doesn't switch off everywhere at once. In some regions, it ends, allowing matter and energy to condense into something like our universe. But in other regions, inflation keeps going. And because inflating regions expand so rapidly, they always produce more inflating space than the regions where inflation ends. The inflating parts of the universe outrun the parts that have settled down. Inflation, in this picture, never stops globally. This is eternal inflation. In this model, inflation is always occurring somewhere. It generates new regions of space continuously. Occasionally, in some small patch, inflation ends, and that patch becomes a separate, isolated region with its own physics, its own fundamental constants, its own version of space-time, a bubble universe. Our observable universe in this picture is one of those bubbles. It formed when inflation ended in our particular region. Everything we've ever seen or measured, every galaxy in those 2 trillion, every star in every galaxy, all of it, one bubble in an endlessly inflating sea. And the other bubbles are not accessible. Not because we lack the technology, because they are causally disconnected from us. The space between our bubble and any other is inflating faster than light can cross it. There is no signal, no probe, no observation that could ever bridge that gap. If a civilization exists in another bubble universe with completely different laws of physics, they cannot know we exist. we cannot know they exist. The separation is not a matter of distance, it's a matter of the structure of space-time itself. This is where the theory becomes genuinely difficult to evaluate as science. A theory that makes no testable predictions isn't a scientific theory in the usual sense. It's a framework. And some physicists argue that eternal inflation crosses that line. If we can never observe another bubble universe, never detect its influence, never gather any data that would distinguish a universe with eternal inflation from one without it, then what exactly is the theory predicting? Others argue that this criticism misses the point. Eternal inflation doesn't just assert that other universes exist. It emerges naturally from inflationary models that were developed to explain things we can observe: the flatness, the uniformity, the absence of monopoles. If the underlying physics is correct, eternal inflation follows as a consequence. The other bubbles may be unobservable, but the mechanism that produces them leaves fingerprints we can study. The internal consistency of the framework and its ability to account for observed features of our universe makes it worth taking seriously even without direct confirmation. There's also a more uncomfortable implication. If other bubble universes exist and each forms with its own set of physical constants, then the specific constants we observe in our universe, the mass of an electron, the strength of gravity, the cosmological constant, might not be fundamental. They might just be the values our bubble happened to land on. Some physicists find this deeply unsatisfying. It means the constants we measure aren't explaining anything deep about reality, they're just the local conditions. Others find it clarifying. It reframes fine-tuning arguments entirely. What eternal inflation does to the question of whether space ends is hard to overstate. In this framework, space is not just infinite, it's generative. It keeps producing new regions, new universes, new space-time, indefinitely. The question of whether space ends can't be answered by looking outward from within our bubble. Whatever answer we find applies only here. Outside, the inflating sea continues, producing structure on scales that make our observable universe look like a grain of sand. We are not just small within our universe. We may be small within a structure our universe is itself embedded in. If eternal inflation is correct, space doesn't just go on forever. It spawns new universes forever. And the question of whether space ends becomes almost meaningless. Even if space doesn't end in the way we imagine, no wall, no boundary, no edge to press your hand against, the universe still has a fate. And understanding that fate brings us back to the original question in a different way. Because if the universe eventually reaches some final state, some end point of activity or change, does that count as an ending? Is that the answer we were looking for? The short answer is no, not really. But the long answer is one of the strangest things physics has ever worked out. The universe has multiple possible futures, and scientists have spent decades debating which one is correct. Some are more favored than others, some are barely considered anymore, but all of them are grounded in real physics, real observations, and real mathematics. The scenario that most cosmologists currently favor is called the Big Freeze. Sometimes it's called heat death. Both names point at the same idea. The universe keeps expanding, as it's been doing since the Big Bang. Gravity holds galaxies together locally, but on the largest scales, space just keeps stretching. Stars keep forming, burning, and dying. But eventually the raw material runs out. The gas clouds that collapse into new stars will be consumed. The universe has a finite supply of fuel, and it's been spending that fuel for 13.8 billion years already. Astronomers estimate that stars will continue forming for roughly another 100 trillion years. 100 trillion years. Our sun will have been dead for longer than we can meaningfully imagine, before the last stars flicker out. After the stars are gone, what's left? White dwarfs, neutron stars, black holes. These are the remnants of stellar death, and they don't burn fuel the way stars do. They just exist, they cool. White dwarfs will slowly radiate their remaining heat into space over unimaginable stretches of time, eventually becoming cold, dark objects called black dwarfs, though none exist yet because the universe isn't old enough. Black holes will endure longer than almost anything else, but not forever. Stephen Hawking showed mathematically that black holes slowly leak energy through a process now called Hawking radiation. They lose mass, very slowly, over timescales that dwarf everything else we've discussed. A stellar mass black hole takes roughly 10 to the 67th power years to evaporate completely. The supermassive black holes at the centers of galaxies would take 10 to the 100th power years. That number has a name, a googol, one followed by 100 zeros. Think about what that means. The universe is currently 13.8 billion years old. That's roughly 10 to the 10th power years. The last black holes won't finish evaporating for 10 to the 100th power years. The gap between now and then is incomprehensible. It makes the current age of the universe look like a single frame in a film that runs for longer than you can express with ordinary language. And when that last black hole is gone, what remains? A cold, dark, expanding void. Photons too low energy to interact with anything. A universe in a state of maximum entropy, where every region is the same temperature as every other region, where no energy can flow from one place to another, where nothing can happen. Not violently, not dramatically, just silence. Endless, cold silence spreading through infinite space. This is what physicists mean by maximum entropy. It's not a collapse, it's not an explosion. It's the universe running out of differences. Heat flows from hot to cold. Energy flows from high concentration to low concentration. Everything interesting in the universe, every star, every storm, every thought, runs on differences. The big freeze isn't the universe ending. It's the universe reaching a state where nothing interesting can ever happen again. Space is still there. It's just empty. Uniformly, completely, permanently empty. But the big freeze isn't the only scenario. There's another possibility driven by dark energy. We know the expansion of the universe is accelerating. Dark energy is pushing space apart faster and faster. Right now, that acceleration is gradual. Galaxies are drifting apart, but they're not being torn to pieces. However, some models of dark energy suggest that it might not stay constant. If dark energy strengthens over time, the acceleration could increase without limit. This leads to a scenario called the Big Rip. Galaxies get shredded apart as the space inside them expands faster than gravity can hold them together. Then solar systems, then planets. Eventually, individual atoms can't hold themselves together. The fundamental forces lose the battle against expansion. Everything is ripped apart at the quantum level. The Big Rip, if it happens, would occur in a finite time. Current estimates put it at roughly 22 billion years from now, though this depends on assumptions about how dark energy behaves. Space doesn't end in the Big Rip either. It just tears everything in it apart until nothing structured remains. Then there's the Big Crunch. This was a more popular scenario before we discovered that the universe's expansion was accelerating. The idea is that gravity eventually wins. The expansion slows, stops, and reverses. Galaxies begin moving toward each other. The universe contracts. Everything collapses back toward a single point, a mirror image of the Big Bang running in reverse. Temperatures rise as everything compresses. Stars merge. Matter dissolves back into fundamental particles. Eventually, a singularity forms. The universe ends the way it began, compressed to an unimaginable density, with our current physics unable to describe what comes next. The Big Crunch is now considered unlikely, given what we know about dark energy, but it's not completely ruled out. If dark energy ever weakens or reverses, the math changes. Some physicists take the Big Crunch one step further. They call it the Big Bounce. In this version, the collapse doesn't end at a singularity. Something stops it, possibly quantum effects that become significant at extreme densities, and the universe rebounds into a new expansion, a new Big Bang, a new universe, possibly with different physical constants, different initial conditions, different everything. In this model, our universe might be one cycle in an endless series: born, expanding, contracting, bouncing, beginning again. This is deeply speculative. We don't have strong observational evidence for it, but it's a legitimate idea within theoretical physics, and it raises an unsettling implication. If the Big Bounce is real, then the question of whether space ends becomes almost meaningless. Space never ends, it just resets. Here's what connects all of these scenarios to the question we've been asking. In none of them does space reach a wall. In none of them does the universe stop existing as space. Even in the Big Crunch, space collapses into a singularity. But a singularity isn't a place where space ends and something else begins. It's a place where our equations stop working. In the Big Freeze, space continues expanding forever, becoming emptier and darker but never stopping, never hitting a boundary. In the Big Rip, space itself is the force doing the ripping. It becomes more space, not less. The universe doesn't end. It transforms. It empties. It goes quiet. The timescales involved here are worth sitting with for a moment. Stars burn out in 100 trillion years. Black holes evaporate in a googol years. If the Big Freeze is correct, space will be expanding and cooling for longer than any number we use in everyday life can express. Longer than a googol years. Longer than a googolplex years. There's no clean way to write it. The universe persists through all of it, just emptier, colder, and less eventful than it is right now. What we're living in, this period of stars and galaxies and planets and life, is the interesting part. The brief, bright middle of a story with an extraordinarily long, quiet ending. None of these futures contain an edge. None of them produce a moment where someone could point at a location and say, "This is where space stops." The geometry we explored earlier, flat, spherical, hyperbolic, plays a role in which fate unfolds. A flat or open universe is almost certainly going to expand forever towards something like the Big Freeze. A closed spherical universe might recollapse into a Big Crunch. But in either case, space itself persists through the process. Space doesn't end, it just becomes empty. And empty space, as far as we can tell, goes on forever. Let's come back to the question we started with. Does space ever end? We've spent a lot of time building up to this moment. We've looked at the geometry of space, the cosmic microwave background, the expansion of the universe, the fate of everything that exists. And now we're back where we started. The same question, the same 4 words. Does space ever end? The honest answer is that we don't know. Not in the way scientists don't know which came first, where more data would settle it. We don't know in a deeper way. We may never know. The universe may simply be too large and our position within it too limited for a definitive answer to ever reach us. That's not a failure of science. That's an honest account of our situation. Think about what kind of creature is even capable of asking this question. You are a biological organism. Your brain evolved over millions of years to solve problems on the surface of a small rocky planet. Find food, avoid predators, navigate terrain, recognize faces. These are the problems your brain was built for. None of them required understanding the topology of space. None of them required knowing whether the universe is finite or infinite. And yet here you are, capable of forming the question, capable of following the reasoning, capable of feeling the weight of an answer that might be beyond our reach. That's not nothing. That's extraordinary. We built telescopes that can detect light from 13.8 billion years ago. We launched satellites that measured the temperature of the cosmic microwave background to a precision of 1 part in 100,000. We developed mathematics that describes the curvature of space itself and equations that break down at the very beginning of time. We did all of this from the surface of a planet orbiting an ordinary star, in an ordinary galaxy, somewhere in the middle of an observable universe that is 93 billion light-years across, and we got real answers. Incomplete answers. Provisional answers. But real ones. What we know is this. The observable universe spans roughly 93 billion light years in diameter. It contains an estimated 2 trillion galaxies. Each of those galaxies contains hundreds of billions of stars. The light from the edge of our observable region left its source before Earth existed, before the Sun ignited, before our solar system had formed from the remnants of older stars. And everything we've described, every galaxy, every star, every particle of gas drifting in the void, represents only the portion of the universe we're physically capable of seeing. Beyond that boundary, space almost certainly continues. How far? We can't say. The measurements point toward a flat universe, flat to within 0.4%. That's a remarkably precise result. It tells us that parallel lines in our region of space stay parallel, that triangles have angles adding up to 180 degrees. That standard geometry holds, but flat doesn't tell us whether space goes on forever or whether it curves back on itself in some higher dimensional topology we can't yet detect. The universe could be infinite, or it could be finite, vastly larger than what we can see, folded in on itself like the surface of an enormous sphere. Both are consistent with what we've measured. We're choosing between two answers we can't distinguish yet. These two possibilities, infinite or finite but vast, have different implications that are worth sitting with for a moment. An infinite universe means that space extends without limit in all directions, that there is truly nowhere it stops. A finite but enormous universe means that if you somehow travelled in a straight line for long enough, you would eventually arrive back at your starting point, like circumnavigating a globe but in 4 dimensions instead of 3. Neither option involves a boundary in the traditional sense. Neither one answers the question with a simple yes, space ends here. The distinction matters philosophically, but observationally, at our current level of precision, both models make nearly identical predictions. We would need far more data than we currently possess to hear. Differentiate between them with confidence. Future observations might change this calculus, but for now, both remain viable interpretations of the cosmos. There is no wall. That much we can say with some confidence. If space ended at a physical boundary, what would be on the other side? If the answer is nothing, then nothing is still a location, and the question just moves back one step. There is no edge you could fly a spaceship to and press your hand against. There is no point in any direction where space gives way to something else. Every cosmological model we take seriously, every geometry, every topology, describes a universe without a boundary of that kind. The universe doesn't stop. It either goes on forever, or it curves back on itself so that continuing in one direction eventually brings you back to where you started. Neither of those is an ending. Not really. And here's what makes this strange to sit with. Every direction you can point right now contains more space. Straight up through the ceiling, out through the floor, north, south, east, west, every diagonal in between. In every direction, beyond the atmosphere, beyond the solar system, beyond the Milky Way, beyond the local group, beyond the visible universe, space continues. More galaxies, more stars, more gas clouds, more of the fabric of existence itself, stretching outward to a distance we can't measure, and possibly can't even define. This is not a poetic description. It's the most literal statement we can make based on current evidence. An infinite universe is difficult to hold in your head. Genuinely difficult. Not the way a difficult math problem is hard. The way a concept that exceeds the capacity of human intuition is hard. You can follow the logic, you can understand the implications, but you can't actually visualize infinity. Your brain tops out. It tries to build a picture and runs into a wall that isn't there. An infinite universe means infinite matter, infinite galaxies, infinite arrangements of everything that can exist. It means every configuration of particles that is physically possible happens, somewhere, an infinite number of times. That's not science fiction. That's what infinity applied to physics actually implies. It's deeply uncomfortable, and it might be true. The implications of infinity extend even further into the strange. If the universe is truly infinite, then there are an infinite number of versions of you out there, living versions of your life with different outcomes. Every possible variation of events that could happen, given the finite number of ways particles can be arranged, has already happened somewhere in an infinite cosmos. This is sometimes called the infinite universe theory, and while it's mathematically consistent with our current understanding, it remains deeply speculative. We have no observational way to confirm or deny it, since those other instances of you exist beyond our observable horizon, causally disconnected from us. It's a prediction that emerges naturally from the mathematics, but it remains untestable, at least with our current technology and understanding. Even if the universe is finite, the scale is staggering. If space curves back on itself like the surface of a sphere, the total volume of that sphere must be at least hundreds of times larger than our observable region. Otherwise, we'd have detected signs of it already in the cosmic microwave background. We'd see repeating patterns in the sky. We'd find the same regions appearing in multiple directions. We've looked for that. We haven't found it convincingly. So if the universe is finite, it's enormous, far beyond anything we can observe, far beyond anything we can meaningfully imagine. What we're left with is this. The universe is at least 93 billion light-years across in the portion we can see, probably much larger, possibly infinite, possibly topologically closed in ways we haven't detected. There is no physical edge. There is no outside. There is no boundary where space stops and something else begins. The universe isn't floating in a larger emptiness. The universe is everything. There is no container. Space itself is the thing. That might feel unsatisfying. You came here wanting a clean answer. Does space itself is the thing? That might feel unsatisfying. You came here wanting a clean answer. Does space end or doesn't it? And the response from science is careful and honest. We don't think it ends. The evidence points that direction, but we can't be certain, because certainty would require information from beyond our observable horizon, and that information cannot reach us. Not now, possibly not ever. Some questions sit permanently at the edge of what we can know. This one might be among them. But there's something worth noticing about the fact that we can ask it at all. Every generation of humans that has ever lived has looked up at the night sky and wondered what was out there. For most of human history, we had almost nothing. No tools, no framework, no way to translate the wondering into actual knowledge. We had stories. We had mythology. We had our best guesses about fires in the sky. And then, over a few hundred years, something changed. We built instruments. We developed mathematics. We sent telescopes into orbit. We measured the temperature of the oldest light in the universe. We mapped the geometry of space across billions of light years. We didn't get a complete answer, but we got further than any generation before us ever thought possible. And the people who come after us will go further still. The next time you stand outside at night and look up, remember that every direction you look, space keeps going, and nobody, anywhere in the universe, has found the end of it yet.